All right. So, get started. Actually, I did have some things I want to mention before we get going here. So, next week, I'll explain a little bit more about kind of the exam on Monday. But on Wednesday, we're supposed to have one of those study days. So, I'm not going to have class. Like, you don't have to show up. You don't have to be on Zoom live, but I am going to post a video Wednesday, and I will have a Zoom link pulled up. I'm probably going to do it at the same time as my other section. So I'll probably be live, and I'll post on Canvas when, but I'll probably be live at 12 instead of 1. But it's basically just an additional video of me working through practice problems. So you don't have to show up, or you don't have to kind of log on via Zoom. But I do want to make that resource just another, set of problems of me working through. So I have another resource kind of going into that exam next week. So I want to mention that because I know that study day is coming up. Also for the Excels, some problems grading the sections I've noticed is when you do the Excel assignments, I need you to upload a file that shows me all of your work. So I can see the formulas. Some of you, for whatever reason, I don't know if you're working off of like a shared license or something, but I can't see all of your formulas. I could see some of them I couldn't. Moving forward, if I can't see the work that you did in Excel and it's just a number, I can't give full credit for that. So make sure the file you're uploading is in fact kind of, you didn't copy and paste any of the values. Some people uploaded a Word document where I can tell they did the work in Excel, but they copied and pasted what they had in Excel, and then I can't see the formulas and the work that you did. So especially if you get stuff wrong, I can't really give any partial credit that way either. So moving forward, let's kind of make sure we do a better job of that. Okay. Any questions from me before we kind of jump into things today? So we left off with a binomial last class. We worked through a bunch of Excel examples. So the last kind of new material we'll go through is today. Next week will be all kind of review for the exam, but we've got another type of discrete random variable, which is the Poisson distribution. Okay? So the setup is that we're going to be looking at certain numbers of events occurring over a given time interval or over a given some space interval. Right? For all the examples that you'll see on the exam, there'll always be time intervals. I'll go through one today, which isn't time, and kind of explain why it might be useful, more so outside the context of like business majors. And we're going to be looking for the probability that we see certain numbers of occurrences over these intervals, right? Now, all these intervals have to be the same length. This could be something like, I'm looking for the probability of the number of crashes on McGalliard over the next week. The week is my time interval. Now, I have to make sure that the intervals I'm looking at aren't overlapping. So if I want to start thinking about the probability of different weeks, I need to be thinking about the 52 individual weeks in the year and not like, have any of those weeks overlap. Now, I'm never going to try to trick you with this, but just kind of giving you this setup for these examples. So how many times do we see these events occur? How many crashes maybe do I see on McGalliard over that expected interval or over the next week? Okay. So if that's our setup, right, we're going to have a probability mass function that starts to give us these probabilities, just like we did for the binomial. Right? So I've got the probability that x is equal to a certain value, right, is this function. Now, there's fewer components to this function than there is to the binomial, and honestly, it's a little bit easier to use, and I think we'll see that by the end of the class. So lambda here, this Greek letter lambda, simply represents the average number of occurrences we usually see over that interval. Okay? So my car crash example would be like, on average, there are 3 crashes on McGalliard every week, right? That would be my lambda, and I want to know what's the probability that I see 5 this week, so my x would be 5 there. So we've already talked about factorials, which another good reason why you should figure out where this is at in your calculator and reach out to me if you can. Okay. The only thing we don't know is this this letter E here. Okay. So all E is it's kind of like pi. It's this number that goes out super far decimal point. But if we wanted to kind of show it to the 5th decimal, it's 2.7182. So if you can't find this on your calculator, usually it's like you have to hit the second key, and then it's like above one of the other original buttons. But if you can't find it, you could use this out to the 5th decimal and get a pretty good approximation. Just like the factorial button, I strongly suggest you find out where this is on your calculator early, and if you can't find it, send me an email, and I can try to help you out. Okay? But once I have that down, it's really the same process as what I was doing with the binomial. Once I identify what my x and what my lambda are, it's just a matter of getting them plugged in this equation and plugging them into my calculator. Okay? So, and I said f of x here. I think in the slides I had this written as f of x. But we're really thinking about it's a function, right? It is f of x, but specifically it's telling us the probability this random variable x is equal to whatever number of occurrences that we want to find the probability of. Okay. So kind of a motivating example. I'm not going to try with this guy's name, but he wrote a book called The Law of Small Numbers, which is really influential in mathematics and statistics. And one of the kind of things that he uses as an example, a motivating example, is he was saying that 0.61 soldiers on average were getting kicked to death by horses in the Prussian cavalry, right? So on average, over a time interval of a year, we were seeing the number of deaths, the average was 0.61. So here, this would be our lambda. And then you might pose the question, well, this probably is a little bit more relevant to today's times, but if you were liable or if you had to kind of pay the family every time that there was a death and you're interested, well, we got to make sure we have enough money on hand. If instead of, 0.61 people die, if 3 soldiers died, would we have enough, money to reimburse or kind of give to these families, right? Not reimburse, kind of compensation, right? So I might want to find what's the probability I lose 3 soldiers this year. So this would be my x value, right? So I've got my lambda, was the average I typically saw was 0.61 deaths. I want to find the probability that exactly 3 occur this next year, right? Same time interval, right? So 1 year. It's just a matter of getting those plugged in, right? So here's my general form of the equation. I plug in lambda, I plug in x, right? And now it's just a matter of getting this entered into my calculator, right? If I do the math here, I end up with 0.02, okay? Which kind of makes sense. Should be a pretty low probability. If the average is 0.61, that means that, usually either 0 people die or 1 person dies, right? Those are probably the most likely outcomes. By the time I get to even 3, it's just going to be pretty unlikely, right? A 2% chance here of occurring. All right, any questions on that before we move to the next example? Okay. So I'm setting us up for some more complicated stuff with this Poisson, but this one should be pretty easy too. So let's say I have this hospital and the number of births that occur every hour is 1.25. Okay? So what's the probability that I see exactly 3 births occur in this next hour? Well, the average rate I see is 1.25. The probability I see, or I want to find the number of occurrences I want to find the probability of is 3. So x is 3, lambda is 1.25. Once again, just a matter of getting that plugged into our equation, okay? Now, one thing to be careful of is if you do e to the, or this number e is to the negative lambda, right? Negative 1.25. If you forget to do that, I'll kind of show you what happens, right? So in Excel, and this is just, I'm not going to necessarily have this on any of the Excel homeworks or anything, but that e value is actually exp in Excel. So if we take e, let's say we went to the negative 1.25, right? We could get that value. If I do e to the 1.25, it starts to get above 1. Well, remember, we're looking for a probability. So if you forget to put that negative sign in there, more likely than not, you'll be able to figure it out because you're going to end up with something above 1, which we're looking for a probability. It can't be above 1. Right? But it's kind of highlighting there, it's e to the negative lambda. Okay? So if we compute this, there's about a 9% chance of occurring. So, if the setup is, that on average 1.25 births occur. So I've got the doctors, the nurses on staff. They're usually, handling 1 or 2 births. But if I have 3 births, in the next hour, I'm going to need a little, I'm going to need another doctor. I'm going to need another nurse there. So maybe if the probability is high enough, I start to have somebody on call, right? If the probability here we end up computing is 0.09, well, maybe that's high enough where I don't want to risk it, right? If there's a 10%, almost a 10% chance of this occurring, I want to make sure I'm going to have the staff available, right? So you can kind of think about, staffing decisions. This Poisson distribution become really important. Okay? What if instead I want the probability that we see 2 or more births in an hour? Okay. So first, I'm going to go here. Switch over to the dot cam here real quick. There we go. So what we're looking for is the probability that 2 or more births occur. So this random variable x, we're saying, is it greater than or equal to 2? 2 or more. Well, first of all, we can start to think about this distribution and the number of occurrences that we're seeing. For the Poisson distribution, I'm going to kind of jump ahead a little bit, but the average rate, right, that was lambda. So if we think about what our mean is, well, the mean is kind of the average outcome that we see. We had a mean of lambda of 1.25. So the mean number of births we see is 1.25 births. Now that's our mean. So just like with a binomial, if we're thinking about all these different outcomes that we could see, 0, 1, 2, 3, 4, well here, it just keeps going, right? I mean, theoretically, I guess this stops at the total number of women who could have children in that around that hospital. But if we're in somewhere like Chicago, right, this just kind of continues. So 1.25 is the mean. So we know that 1 and 2 are going to be some of the more likely outcomes, right? So 1 and 2 are some of the more likely outcomes. And as we move away from that 1.25 value, the probability of seeing these outcomes, right, starts to decrease. Same idea as what we talked about Wednesday with the binomial. So if I want the probability x is greater than or equal to 2, well, it includes one of the more likely outcomes, as well as all these outcomes here. Now, granted, these probabilities start to get really, really small, but if I'm adding all these up, I'm probably going to be not very close to 0, right? I'm including one of the most likely outcomes as well as a lot of these other outcomes. And so I think one of the answers on the slide there was like 0.03 was a possible answer. Well, that doesn't make a lot of sense for what we're doing, right? That's a pretty low probability. Maybe the probability I see 5 births in an hour is something like 0.03. But the probability I see 2 or more, any of these, probably going to be substantially larger or further away from 0. Excuse me. So I'm like, okay, well, even if I can rule one of the answers out, I still have to compute this, right? Well, just like the binomial, if we have one of these greater than or less than signs, we think about what outcomes fit this criteria. So if I want the probability x is greater than or equal to 2, I would take the probability x is equal to 2, right? That's the very first outcome that fits that criteria, plus the probability x is equal to 3, that's the next outcome, plus the probability x is equal to 4, plus I keep going, and I said, where do I stop? Right? Now, every time I want to find one of these probabilities, I'd have to use the Poisson distribution. So even if I could find that stopping point, and I don't know, it was like x is equal to like 100, I don't want to have to use that Poisson equation that many times. Well, just like the binomial, right, there's an easier way we can do this, right? So if I think about, I'm trying to find the probability of this event, and we call that event A, I know that's the same thing as 1 minus A complement, okay? So if x is being greater than or equal to 2 is A complement would just be that x is less than 2. Oh, sorry, my thumb's covering up the 1. But yeah, x is less than 2. So I then think about, okay, what are all the possible outcomes that fit this criteria? Well, what's the very first one? Remember, this is discrete. So the very first outcome that is less than 2 would actually be seeing that x is equal to 1. Okay. And I would also add, what's the other outcome that would meet that criteria? Probably that x is equal to 0, right? We can't forget about, we could see something that occurred 0 times. Okay? So now I only have to use that Poisson equation twice, and then once I have those two probabilities, just subtract them from 1. Okay? Any questions there? And let me, let's go here. I'll leave this up down here. You're still kind of working on it. I'm going to go back here, and then for you, I think I gotta hit this button real quick. We're waiting for the slide here. Give me 1 second. There we go. So this was kind of the answer I said didn't make a whole lot of sense, right? This 0.03. We talked about what we really need to do is kind of 1 minus these two probabilities. So I just use x equal to 0, plug in my lambda of 1.25, x of 0, compute that probability, plug in my x equal to 1, same lambda, get that probability, add them up and subtract them from 1. Right, so we get about 0.35 there. So there's a 35% chance I see 2 or more births, right? So I better, it's a pretty high probability. I want to make sure I have enough staff that, I can handle 2 or more births, okay? Now, one thing I want to point out here as well, kind of similar to the binomial, some things we talked about, this actually simplifies quite a bit. Notice anything to the 0 power we said was 1. 0 factorial and 1 factorial are also both 1. So in fact, in this one, you can kind of ignore anything that's 1, right? Multiplying or dividing by anything that's 1 doesn't change it. So this is really just e to the negative 1.25. In fact, I think when I did this in Excel, I kind of proved that to you, right? E to the negative 1.5 is all I did here. And that's exactly what it ends up being because these two things are just equal to 1, okay? Just kind of reiterating that. Are there any questions over any part of that process? Because with the Poisson, using this complement rule becomes really important because honestly, you can't really do this by hand, especially if you're limited in time like on an exam, right? You need to know how to be able to use that complement rule to solve for these probabilities, okay? All right, get rid of that now. So we'll keep going. Just for those of you on Zoom, if you're still have this pulled up, make it a little bit easier. So I showed you slides similar to this for the binomial last class, but here's kind of 4 different Poisson distributions. Notice when we have a mean that's really low, like 0.1, well, the probability, if 0.1 is the average, more often than not, we're going to be seeing zeros. I mean, the probability of seeing 2s and 3s are relatively low, and those will pull the mean up a bit. But if our mean is really, really low, like 0.1, we're typically going to be seeing 0 a lot. So here, right, the probability to see 0 for this Poisson distribution is about, what, 0.9 or 90% of the time. As that mean gets higher, notice, well, with a mean of 0.5, 0 becomes a little bit less likely, and now it's more likely we also see 1 sometimes, right? And then the probabilities of the, higher outcomes increase a little bit as well. Now, this is where it kind of gets a little weird, but if I had a Poisson with a mean of 2, so I would think 2 is the most likely outcome, right? Well, it is, but it's also tied with the probability I see 1. Right? So why might that be the case? So if we think about the mean, right, lambda, the probability of these different outcomes, the mean is influenced by high values, right? So when we have higher values start to become a little bit more likely, they're going to pull the mean up. But there aren't values on the left, right? We're stopping at 0. We can't see negative occurrences of something. And so the mean is going to be influenced a little bit by these higher values, and that's why 2 isn't the most likely. It's tied with the most likely here. Same kind of idea here if we had a mean of 5. 5 is the most likely outcome, but it's tied with 4. And that's because our mean's kind of being pulled up a little bit by these higher values. Now, as we move away from that mean, in either direction, notice the probabilities start to fall, right? The mean here was 2. We move away from that, the probabilities start to fall. Unlike the binomial, which kind of whether or not it was left, right, skewed, or a normal, depended on the mean of the Poisson is always going to be, the Poisson's always going to be right skewed, right? We're always going to have a longer right tail because we have to stop at 0. Theoretically, on the other side, we can kind of see this go off into not quite infinity, but extremely, extremely high values. Okay. So with the mean here, we're thinking about we're going to have, doesn't matter what the mean is, we've got these right skewed distributions, like long right tails. Okay. So knowing that mean is simply whatever the average rate is or whatever lambda is, a really unique property of the Poisson is that the variance is also lambda. So if you go through, you took every outcome 0 minus that mean of lambda, so 0 minus lambda squared, multiply by the probability I see 0, plus 1 minus lambda squared times the probability I see 1, all the way through every single possible outcome. The mathematical proof that you can kind of, you kind of simplify things, you can prove mathematically that the variance will always be lambda. Okay? So it's kind of a unique feature of the Poisson distribution that the mean and the variance are actually the exact same thing, which means the standard deviation is simply just taking the square root of the variance, right? So the square root of the variance, just the square root of lambda for the standard deviation, just like every other variance and standard deviation we've talked about. Okay. So just like just kind of a unique property. We won't really exploit it a lot in this class, but as you kind of move, forward in statistics, what you find is that quite often this Poisson distribution is useful because of this property that the mean and the variance are the exact same. So let's try to kind of relate what we talked about with the binomial to the Poisson distribution. So I probably wouldn't expect you to be able to do an example like this on the exam, maybe on like the Connect homework, but it's also something that allows us to think about future distributions we'll talk about after this first exam. But so let's say I've got 10,000 different atoms, right? And I know the probability that any one atom decays in the next minute is 0.0005. So what's the probability I see 3 atoms decay in this next minute? Well, this one's kind of set up as a binomial, right? We've got a finite kind of number of trials, 10,000 different atoms. The probability of success, or the probability that any one atom decays, is 0.0005. And I want to find the probability that I see 3 successes, right? 3 atoms decay. So I plug that in. My n is 10,000, my x is 3, and my p, or my probability of success there, is 0.005. So I plug those 3 things into my binomial equation. I've got something that looks like this. I mean, even if I cancel things here, I'm still going to have 10,000 times 9,999 times 9,998 divided by 3 times 2. So I'm still going to have a very large number. If instead of looking at 3 atoms decaying, I wanted something like 9 or 10, this number could still be very large. And maybe I'm having some issues handling it in my calculator. Now, I can't actually compute this one. I get 0.14037. But this is, kind of messy and not really easy to do on my calculator. If I ever have a large number of trials, right? So n is really large, and my probability of success is really, really small, right? So if those 2 things are true, number of trials is really large, probability of success is pretty small, I can actually use the Poisson distribution to approximate what the binomial probability mass function would give me. Now, it won't be perfect, but it's going to be a very, very close approximation. So what I'll do is I know how to calculate the mean for a binomial. That's just n times p. So for us, that would be what? 10,000 times 0.0005. So we can compute that mean for our binomial, and we'll just use it as the mean for our Poisson. Okay? So through some fancy math, we can show that that distribution, the Poisson distribution, would be a very close approximation to what we were getting with our probability mass function from the binomial. Okay, so I'll kind of show that to you. So we first compute our mean of the binomial, 10,000 times 0.005, and we get 5. We'll use that as lambda. We're still looking for the probability that 3 atoms decay, so lambda is 5, x is 3. This is a lot easier to put into our calculator, right? And it gets the exact same answer. Now, it's the same answer to the 5th decimal. That's why I have an approximation sign here. If you go out far enough, it's going to be a little off. But this is just like the first example where we'll talk about sometimes we can use other distributions to approximate what another distribution might give us, right? And this is one of those scenarios, okay? Any questions on this before I keep moving? Got a chat. Okay. Also, if the audio ever anything starts sounding weird, let me know. I can reset it. I always worry about that since I sometimes have these issues. So let's talk about, kind of like last class, what are some of these scenarios that would not be possible to use the Poisson distribution for? So first one, we've got the probability that we see a certain number of accidents occur on a highway over a given day. Well, I've already kind of used this example. This one is you kind of think about our time interval is a day. we're looking for the number of occurrences of accidents, this one would be a perfect situation to use the Poisson. Second one, the probability of stock return exceeds 10% in a given year. Well, what are my occurrences? I've got my time interval over a given year. What are my occurrences here? Well, I can only ever see this exceed 10% one time. It's just one, right? I don't have really any other possible outcomes here. Okay? I could see it not, or I could see it not return 10%, or I see it. So we aren't looking for the number of occurrences here, right? It's not like we said the probability that a stock return exceeds 10%, how many times in the next 20 years or something like that, right? So this one doesn't really, we're not looking for a certain number of occurrences, so we can't use the Poisson distribution, right? What about we want the probability of a certain number of calls to a call center in a given minute, or time intervals a minute? We're looking for the number of occurrences, the number of calls that come in. Perfect example to use the Poisson. What's the probability we see a certain number of insurance claims over the year, over a month, some time period? Once again, we want the number of occurrences of these claims, right? So those kind of two make sense for the Poisson as well. Now, this is a pretty real world, or good, very applicable thing where, if I think I'm going to have to pay out to a certain number of claims, I want to make sure I have enough money on hand to be able to do that. And so I want to know the probability, like if I can figure out the claim at which I wouldn't have enough money to pay them out, I want to see if the probability of getting to that number of claims is really high or really low. Because if it's really high, I'm in trouble, right? If it's really low, then I've got plenty of resources on hand to deal with it. Any questions on any of those before we keep moving here? All right. So I'm going to work through an example now that's a little bit unlike what I would ask you on your exams, only because it's not a time interval. Okay. But it's still important that we know that this exists. So these non-time interval examples. So there's this guy, W.S. Gazette. I think his name's William, but that might be wrong. And he was a brewer for Guinness in turn of the century. No education, like no formal education in math or statistics, but just a really, really smart guy. So as he's working at Guinness, right, they've got these huge vats of beer that they're brewing, these huge vats of liquid, and they want to make sure that the yeast particles per milliliter are what they want, so that the beer, I guess, is created correctly or tastes correctly. I'm not a brewer, but this is a general idea, right? And he starts looking at taking out a little bit of the liquid at a time and measuring how many yeast particles are in each milliliter that he's extracting. And he notices that these particles follow a Poisson distribution, right? So as he's recording these, he finds that there's a mean, right? But sometimes he sees 8, sometimes he sees 9, sometimes he sees 10, right? So the number of particles is kind of like the number of occurrences here. And our time interval is no longer a milliliter. It's no longer an hour at a time, but it's a milliliter, right? It's space. It's an interval of space. So he figures out that it follows this Poisson distribution. He then also kind of extends this to figuring out this other distribution called the student T distribution. Well, why doesn't it get called the Gazette distribution? Because back then, if you didn't have any kind of formal training, you really weren't given a lot of respect. So he came up, made some really important discoveries, made a lot of money. So that's why I kind of has a little necklace here or whatever, but this gives us a nice setup for a Poisson distribution example, right? He's got this huge vat of liquid, and he looks at kind of these milliliters, right? He knows that when he looks at this 1 milliliter, he sees 10 yeast particles per milliliter, right? So what he's thinking about, he says, okay, I know that on average, I'm taking out these milliliters, and I see that the average is 10 yeast particles per milliliter. If I were to pull out 1 more milliliter, what's the probability I then see only 8 particles? And these particles are really like our number of occurrences, right? And our milliliter is now our space, our interval. So on average, we see 10 particles from our samples. So what's the probability the next sample I take, I only see 8, right? Or kind of in the rest of the liquid that's left, I see 8. Right? Well, I've got my lambda, I've got my number of occurrences I'm interested in finding the probability of. Just a matter of plugging them into that Poisson equation, right? Pun intended there, plug and chug. So lambda is 10, x is 8. Just a matter of getting these entered into our calculator, okay? So I want you to kind of work through some of these, make sure you can reproduce these answers, right? And we can, make sure you can reproduce that 0.1126 using your calculator. Because at this point, like once we get our values plugged in, like I can't like teach or help you at this point unless you start to run into problems as you're working through this, right? I can enter this into a calculator in front of you, but that doesn't do you any good, right? Being able to kind of enter this into a calculator and figuring out if you're having some issues with order of operations or finding that factorial button, that's kind of on you. Just you have to do it, right? You have to kind of try to follow along with these. Okay. Any questions on that one before we keep moving? We have two more things that I want to work through. I think this is we'll leave this. So, have you heard the joke about the Poisson distribution? It's pretty fishy. Poisson means fish in French. But we're going to have one more Poisson example that we work through. So, switch over to this dot cam. So one thing we can do, and I would kind of expect you to know how to do this for the upcoming exam, is let's say, I don't know, 5 people are killed every year being struck by lightning. Okay. Then I say in the U.S. So let's say the probability that I want to find is, well, what's the probability that, I don't know, 2 people are struck and killed by lightning, but when I'm asked this, the word problem says in the next month, right? So I'm thinking about the number of occurrences over a monthly interval, right? I have the average that occurs over a year. So what could I do, right? Well, I can find or convert the average over a year to the average over a month. So if I know that 5 occur every year, how could I find the average number that occur over any given month? Assuming that getting struck by lightning is equally as likely in every month. Yeah, I simply divide by 12. Now, I just got my lambda, I've got my x, so I would take lambda to the x times e to the negative lambda over x factorial. Right? So once I convert it, it's pretty easy. It's just like it was before. So the key there is if I ever want to go, I want to kind of decrease my time interval, right? Going from a larger interval year to a month. I'm going to divide by some factor. Right? You know what that factor is? Well, how do I go from year to a month? I divide by 12. What if I want to go from a week to a day? Divide by 7. What if I want to go from an hour to a minute? Right? Divide by 60. Right? So I'm never going to give you an example or ask you a question where it's something you wouldn't know, like even something weird like, I don't know, inches to miles, or I don't know, something where it'd be a conversion factor you wouldn't know. In fact, sometimes on the exam, I say something like there are 12 months in a year, right? Something that hopefully everybody knows. But this is the general idea. If I want to go to a smaller time interval, I divide the original lambda I was given to get the lambda that I need, right? To get it into the time interval that I'm looking for the probability of seeing a certain number of occurrences in. What if I had an example where, let's say every minute, and I made fun of myself last class. I think I don't say this a ton, but I said that, let's say every minute I say the word 5 times, okay? What if I want to find the probability that I say the word I don't know, 50 times in the next hour? Okay. Well, I need to find my lambda, or my average rate over an hour. Well, if I'm saying the word 5 times a minute, how many times would I say it in an hour? Simply multiply by 60, right? There's 60 minutes in an hour. Okay. Then I would plug in what? Lambda. So my lambda here is going to be 300 to the what? X, e to the negative lambda over x factorial. Okay. So anytime I want to go to a larger or increase the time interval I'm looking at, that's a situation where I then have to multiply, okay? So it's not too terribly tough. You know, once I just make that conversion, it's just like any other example we were looking at before. Okay. Any questions on that before we keep on going here? Good with that? Okay. All right, I'll leave this up in the bottom corner here for a second as people are kind of finishing up on maybe writing it. So let's go back. I got one more thing. Oh, there we go. So one thing I like in statistics or mathematics in general is anytime we can go against our intuition, right? Anytime we can find a result that doesn't seem intuitive, right? I always kind of think that's useful because a lot of people make decisions based off their intuition. So if we can figure out our intuition is wrong, that's important. So let's say I've got this example where the probability that I want to find the probability that at least two people in a class have the same birthday. So the class size I assume here, you know, I don't think this class has a couple more people, but I assume 35 people. Okay? So in a class of 35, we assume that we don't have any twins or that like nobody's mothers were planning it, you know, have kids at the same time so they can be friends, right? That every birth is independent and that every day is equally as likely to be born on. Okay? So if X is the event that two or more people have the same birthday, what's the probability of X? Well, a lot of people think it's going to be relatively low, right? I mean, out of 35 people, seems a pretty low chance that two people have the same birthday. But I'm probably showing you this for a reason. It's probably not actually as low as you would think. We could also figure out, well, yeah, if I've got a room of 35, you know, maybe the probability is relatively low, but if I've got 1,000 people in a room, well, now the probability someone has the same birthday seems like it'd be relatively high, right? So what's the number of people I need to kind of get to that 50-50 point, right? Such that there's a 50% chance that out of this many people, two people would have the same birthday, right? What's that number of people that would give me that 50% cutoff, okay? So we're gonna kind of switch this around a little bit, right? So let's say X was the probability that two people have this, or X is the event that two people have the same birthday. So X, you know, that's the same thing as 1 minus the probability of the complement. So the complement here, we're using our complement rule, would be that nobody has the same birthday, right? If X is the probability that two or more people have the same birthday, X complement is that everybody has a unique birthday that's different from each other. So what we're gonna do is, I'm gonna line everybody up, right? These 35 people, I go to the very first person, I say, what's the probability that first person has a unique birthday in that group? Well, I haven't asked anybody yet. So there's 365 days available for them to have a birthday. Out of the 365 for them to have a unique birthday. So the probability they have a unique birthday is 1. Then I go to the second person. Well, what's the probability they have a unique birthday? Well, there's 364 other days that they could have a birthday that would be different than the first person. So 364 out of 365. Then to the next person. Well, now there's only 363 days left for them to have a unique birthday. So 363 out of 365. We keep on doing this, right, all the way to the very last person. Okay? So we have all these probabilities that all, you know, for each of these 35 people that have a unique birthday. So if what we think about what we're doing is, we're kind of saying, like, what's the probability that person 1 has a unique birthday, and person 2 has a unique birthday, and person 3 has a unique birthday, all the way to the 35th? Well, if these are independent events, we know that anytime we want to find the probability of the intersection of two independent events, we simply multiply the probability of those events by each other. So this would be the probability the first person has a unique birthday times the probability the second person has a unique birthday, all the way to the very last person, which if we do that, whoops, there we go. Write these numbers out, right? Just what those probabilities were. Actually, this will simplify down to something that looks like this, right? So we could actually rewrite this mathematically. This is kind of a formula that gets used in situations like this, where you look at the number of possible kind of, not always days available, but outcomes available, the size of the group that you're looking at. So this ends up simplifying down to this equation. So if we compute this, we actually end up with 0.186. But remember, X complement was that nobody has the same birthday. So to get the probability that somebody has the same birthday, it's just 1 minus the complement. So there's actually an 81% chance in a group of 35 people that 2 people would have the same birthday. That seems really counterintuitive, but that ends up being what the probability is. And in fact, you only need about 23 people. That 23rd person pushes you over the limit such that in a room of 23 people, the probability 2 people have the same birthday is just over 0.5, right? So like if you were betting on this in a room of 23 people or more, you should always bet that 2 people have the same birthday. I always thought it'd be fun to do that with a group of people. Like even if you had like 50 people in a room, I think a lot of people would take the bet that no one has the same birthday. And we already saw with 35, the probability is already as high as 81%. With 50, we're going to be really, this is a pretty good bet for us, right? So just kind of a fun, unique example that uses some things we've talked about, right? The independence idea that the intersection of events is just the probability of each event multiplied by each other. Our complement rule. All right, so it's kind of a fun example to kind of end things today. Like I said, we'll talk Monday a little bit more about the exam. I would try to start working on those homeworks, get those out of the way as early as possible so you leave next week open to kind of study for that exam. Other than that, I won't do an online quiz for today, so you kind of have the weekend to kind of either take off or the rest of the day to kind of maybe spend a little bit of time on homework. And yeah, have a good weekend, stay safe, and I will see you guys on Monday.